All right, here we go. This is now lecture number 2 here at Absalon in Math 1 for biotech and mechanical folks. We're starting off by solving the problems I wrote on the board at the end of the last video. Task 1, take a look. Second plus 2b. Yes. Minus 12ab. Okay. And it probably says simplify. So we have to try to simplify what's written here. And for that we need to, well, it's suddenly hard. Plus 9bn, that's at the end here. Okay, plus 9bn. Yes, thanks for that. To simplify this problem, you need some algebra skills.
You have to recognize that as the
That's
square.
Something we just talked about. You take the first number squared plus the second number squared plus the double product. Let's start with that.
So this is where it makes sense.
It's a number squared, but you need both 2 and a squared. We saw that last time. It should be a product squared. It's each factor.
So it's really 4 again.
Oh no. And similarly here,
Give
it will
9b squared.
And then I need to get the double product, which is basically the lucky total multiplying that number with that number. And when I point here, I mean the whole 2a. And when I point here, I mean the whole 3b. That means I get plus, because it says plus, the lucky total multiplied 2a, 3b. And the rest here,
anything with it, so I can paste it down.
So minus 4a squared minus 12ab and plus 9b squared. And then we can calculate a bit more on that and see what it gives. And notice that you don't use equivalent symbols when reducing, you use equal signs, because that is for any value of a and b, the same as that, which for any value of a and b is the same as that, the same as that, the same as that. At some point, I can't keep doing it. So no equivalent symbols at that point. By the way, that equal sign is not the same equal sign as like here. And it's probably the first time you're hearing this. That equal sign is a truism equal sign. It means that it's always true, no matter what values you assign to a and b in that equal sign. That equal sign is only true if x is assigned the value 2.
So this is a conditional equal sign.
But it's a truth equal design. So there's a difference, and you get used to looking at it. But back to the story. Now we can see that 4a1 is cancelled out by minus 4a1. And we can see that 9b1 is added to 9b1. So that must give 18b1. And then we can see that here it says 2 times 2, which is 4, and 4 times 3, which is 12, because the order of factors doesn't matter. So I'm allowed to say 2 times 3, and just forget a and b for a moment. So here it's actually 12ab minus 12ab. So they also cancel out with opposite signs. So what we end up with is just 18b squared. And that was the result of the first task. Any questions? So let's take task 2. 5 or 4. Minus b. Okay, minus b. Yes, it's a simplification task. So this equal sign is true for any possible value of a and b. And that means this is not an equation I'm solving, it's not. It's an expression that I'm simplifying. So I should only use the equal sign, not any other signs. So it's equal to that. And that's what this result states. This total sum, subtotal difference, and as we saw last time, it results in the first number squared minus the second number squared. The first number is 5a. And when we square 5a, you must think of squaring both 5 and a, so it equals 25a squared. So I must say minus the second squared, meaning minus b squared, and I haven't changed anything here. So I'll just copy and paste it down. So minus 25a squared minus b squared, and then we can keep on calculating. And make sure when you solve problems to keep the equal signs lined up under each other. That way the paper stays in order, making it much easier to keep track. So I have 25a squared minus 25a squared, they cancel out. And minus b squared, that must be minus 2b squared. Any questions about that? So what do we mean when we say all of that equals minus 2b? And what we mean is no matter what values we put in place of a and b here, it will give a number, And that number is the same as if you just substitute in the b you found there. It doesn't depend on a at all. And maybe you can't see that right away, that this up here doesn't depend on the number a. And that's why we call it simplifying, because it has been simplified down and made prettier. Divided by 3. A third? Did I write a third? Didn't I mean to write a half? That would make more sense, right? Okay. And I also think I'd know myself poorly if I need a step here. Okay, here's the question. Just count the bananas, because here are the squares. Here are 2 more squares, so we have 3 squares total. So you just count how many squares you have. 1 here, 2 more here. That makes 3 squares. So let's move on. There's a minus in 1/2. Yes, that's the same as saying minus squares, because raising to a half is the same as taking the square root, as we last saw. And finally, we can see that a to the 3/2 over a to the 1/2, you subtract. So a to the power of 3/2 minus 1/2. And a to the 3/2 minus 1/2 must be a to 2/2, which is a to the first, so plus 7a. And then we see 3 bananas minus 1 banana gives 2 bananas. So it must give 2 squares. 2 squares. And then plus 7a. We can't really do more, so draw 2 lines under it.
That was okay to subtract. Now, questions?
What I did here was that I took this expression where it says a raised to the power of 3/2 divided by a raised to the power of 1/2. And then I used an exponent rule, which says that it's a raised to that exponent, which is 3/2.
Minus that exponent, which is 1.5.
So here you have 3 bananas minus 1 banana, which gives 2 bananas, meaning 2/2.
Now it will be a raised to 2/2.
But 2/2 is another way to write one.
And a to the first is the same as a itself. So that's why it ends up just being 1 of a.
Any other questions? Yeah, it's all good. I just started from the left and then I just went along. But we really could have looked at the whole lines and then I would have seen that the 2 cancel out right away. So that's absolutely correct. So it was just sloppy from my side. Any other questions? So let's try to do exercise 4. The copy is off. Okay, yes. So again, we can see that the third ace can also be written as a raised to the 1/3. We saw that last time. So basically it just says 1 banana plus 7 more bananas. That must be 8 bananas. So that's the same as 8 times. And what should we say? Should we say a to the 1/3? So we stick to the exponential notation. And then I should say here that dividing this by that must give a to the 2/3 minus 1/3, because I have to subtract the exponents from each other. And if I have 2/3 and need 1/3, then I am down to 1/3. So that means that this whole fraction here just becomes a raised to the 1/3.
So that I can write minus
Raised
6a to a power.
So now it actually just says 8 bananas, 6 of them. How many do you have left? 2, and the bananas raised to the 1/3.
So that's the answer. And if you want to, you could have written it like that. So you might also write 2 times the cube root.
No way. So either like that or like this, whatever you prefer. Yeah, okay, and 5. Like this. Well, again, you just need to realize that a to the power of a half is the same as the square root of a, and it cancels out. And I can add the two exponents, so I get it to the fifth, then it's done.
Now you're cheeky, cheek 6. Like this.
Again, I see it's the same base for several powers multiplied together, so I must add all the exponents. So it says 1, 2, 3, meaning a raised to the 1, 2, 3. And in the denominator, I know you multiply the exponents because it's a power raised to another exponent, giving a to the sixth. And then we can see that here it's something with g0 minus 1 minus 2, that's minus 3 plus 3, that's 0. So it says a to the 0. But we defined last time that it is 1.
So here it's 1 over a to the 6th.
And if you distribute it when writing it, you can also write it as a to the minus 6.
Which isn't a negative number, though it has a negative exponent.
Yes.
That was task 6. So let's see if anyone thinks we should calculate the rest all the way to 15, or is there anyone who should
I'm
calculate?
thinking that it looks like it's raining.
Should I just take them all together and spend time on that? Yes.
Then I can just have the 7 here, I think. How does the 7 sound?
1/2 plus 1/3 over 4.
The whole minus 2 over 24. Okay.
Okay, so first I need to add two fractions, 1/2 and 1/3. This one I rewrite to the essential part by extending the fraction with 3. And here it says 3/6. I also rewrite this one to a number of 6 by extending with 2, so plus 2/6.
And the whole thing should be divided by 4.
And then minus 2/24. I'll just let that stand. So the biggest sin in mathematics is laziness. Make sure to write down the interim calculation so you don't skip too much. Once you're really trained, then you can skip the interim steps. You can afford to skip over them. And I can't afford to skip so much when there's a video
Doing it at the same
camera.
time. So I'll write them down. Okay?
So I have 3 plus 2. That must be 5 shape parts.
So it says 5 rare parts, which should be divided by 4 minus 2/24. So there's a rule that says when you divide a fraction by a number, it's the number times the denominator. So this can be written as 5/24 minus the 2/24. And now I can just add up in the numerator how many I have. 5 bananas minus 2 bananas. That must be 3 bananas. And the bananas are 24. So it's called 3/24.
Any questions about that?
So we erase and move on. Yes, questions over here.
24/0. Ah, I opened it properly again. Yes, of course. That's right. I didn't notice it, but that's right. We usually like to make it with irreducible fractions.
All right. We're now at task 8.
Plus 7 part 8.
Over 2, you need to calculate it.
So I'll start by
And
thinking
that-
that it should be rewritten as a fraction with the denominator 8.
68 and 64, so I can write the number 8 in disguise as 64 markings.
And then plus the 7/8 that are there. And all divided by 2.
So I can just count up how much I have. 64 plus 7 more. That must be 71. So 71/8, which should be divided by 2. And then we have this. We just need to multiply in the denominator. So that must be 71/16, which probably can't be reduced. It's difficult. Did you finish it? We should hear it again.
Half a piece and a proper one, yes.
Minus 3 plus 10 over 2.
Okay, yes. To divide two fractions, you take the first fraction and multiply it by the reciprocal of the second.
And then I should subtract 3 and add 5, as I can see here.
You multiply two fractions by multiplying the numerators together and the denominators together. So here we get 8.5, also called 4. So it's 4 minus 3 plus 5, and 4 minus 3 gives 1, and plus 5 makes 6. So the answer is 6.
Yes, task 10.
Like this.
Okay. Again, we need to put this under a common denominator. So I multiply by 2 and get 4/6. Any objections? Was it written incorrectly according to the task? It's all over 4, so here it should say 4, like that. Okay. Yes, we want a common denominator. You can always find a common denominator by multiplying the two denominators. But sometimes you might also consider if there's a number that both numbers divide into evenly. And the first number that both 2 and 3 divide into is 6. So the common denominator is 6. Here I'll multiply by 2. If I multiply by 2, I get 2 times 2, which is 4, over 3 times 2, which is 6.
Text by Nikolai
Multiply by
Winter.
3. 3 times 5 is 15. So I get negative 15 for one part.
Everything should be divided by 4. And then I need to remember to add 3. So I can say 15 minus the 4, which gives negative 11. So it's negative 11 for one part.
Which should be divided by 4, then plus 3, whole. Then I multiply 4 by 6, giving 24 parts. So minus 11, 24 parts. And then I rewrite that to the amount 24 parts. And then I should say 3 times 24, that's 72. So that's something with 72, 24 parts. Just like that. And then I can just subtract the 11 from the 72, which gives 61. So we get 61 24ths.
Which is our final answer.
Are you all in agreement?
Yes, question 11.
Now we're going to solve equations. All right. What do you have to say now? The number is x plus 1/2. Are you in fourth as well?
Minus x. Then we have to simplify it.
Shut up, I know it's equal to. I think we just need to simplify it. Yeah, we just need to simplify it. Even though I put an x in, we just need to simplify it. Okay, so we're dealing with the square of a binomial, and then we just get started. Square of the first term, plus, always plus. Square of the second term, plus or minus twice the product. In this case, plus. So I get x squared, plus then I have to square this, giving me 1/4. That's 1/2 times 1/2, which is 1/4, when multiplying numerator by numerator, denominator by denominator. Then I need the twice the product, which is 2 times x times 1/2.
And finally, I need to copy and paste the rest. So minus 1/4 and minus x.
Let's see what we get. All in all, it looks like it survives. A quarter cancels with minus a quarter, and 2 times a half gives a whole. So here we have a whole x minus a whole x, they cancel out.
So that means it just ends up giving x squared. And that was task 11. Task 12.
I'm equal to 1 million, okay. So it must be something with 6 zeros. If you need to find an exponent, you must use a logarithm. And which logarithm should I use when the base is 10? I should use the usual logarithm, the common logarithm. The only logarithm where you can omit writing the base is the common logarithm. So I just take the logarithm with base 10, and I won't write it, but that's what I mean. To 10 in power is equal to the logarithm. To 20 in power, and that's because 1 million is the same as 10 to the 6th, because here there are also 6 zeros, so you can write it as 10 to the 6th. And here we've learned that log and 10 cancel each other out as inverse operations. So that's why you just understand what x is now.
x is 10 to the negative 7, but it should give 6.
So what we've answered is, what should 10 be raised to give 1 million? And it should be 6. Yes, exercise 13. Yes, exactly. I was always a bit overly pedagogical, but even if it hadn't matched such a neat number, you would have written like that, right? Here we need to find an exponent, so we need an exponent finder, and we're using the exponent finder that uses the base table.
It's called Euler's constant, and it's named the natural logarithm.
That means I take ln on both sides and find that x is still ln of 8. That was exercise 13.
Any questions? See you today. Have a good trip.
So let's move on to exercise 14. Thanks for tonight.
And we need to find x, notice. Because
When I solve an equation, I use BMT. And that means the equation written here is equivalent to the one that will soon be written here. But the one that will soon be written here is also equivalent to the one that initially stood there. So there needs to be an arrow in both directions, and that's called a bi-implication. You'll need this when solving equations. The first thing I do is divide the equation by 5.
So then you'll have 1850 minus this over here.
And now I need to find an exponent with the base number 3.1. So now I can do two things. I can either take the logarithm to the base of 3.1, and then I'm done. Or I can use ln if my calculator only has the ln button. But I can also use log base 10 if that's the only button I have. But let's say I have a calculator that can work with all logarithms. Then I can directly find x now by taking the logarithm with base 3.1
Raised to the number 18.5d.
and then I'm done. But let's also try solving the equation again by using ln. By doing so, I've actually proven to you that all logarithms are proportional.
And that means if one knows one of them, they know them all.
Let's try taking ln on both sides here. So we've got ln. So 3.1 raised to the power of x is equal to the ln of 18 over 5. And here we can use logarithm rule RE3 from last time. The logarithm of a power is the exponent times the logarithm of the base. That was RE3. Romans calculated RE3 from last time. So this can be written as x times the natural log of 3.1.
And it's still equal to the natural log of 18.5d.
And now I can isolate x by just dividing by this factor. Because this is just a number, it's just a constant. So I can just divide by it. So x
Equals the natural log of 18/5.
over the natural log of 3.1. So if both x equals that, and x also equals that, then that must be the same number as that. Can you see it? So what's the difference between taking the base 3.1 logarithm of 18.5 and taking the natural log of 18.5? What's the difference? The difference is just a factor of 1 over the natural log of 3.1. This is a factor, and that's the difference. But then I've proven that the two logarithms at least are proportional, because one equals the constant times the other, so they are proportional. And this applies to all logarithms. They are proportional. They behave the same except for a proportionality constant. And this means that if you just have a converter with one of them, you can solve all problems involving logarithms. That was a bit deep. Just this story.
Okay, task 15, which I think is the last one.
Yes, so I've just written it with symbols. If I have to solve that equation, I can either use the a number logarithm and find x directly. I just need to take the logarithm that's on base a raised to b, then I'm done.
Or I can now bring L onto both sides and write that x times ln of a
Is the same as ln of b, and then solve the case for x.
It becomes ln b over ln a.
Now notice that this is the same as that. And now I've actually proven it.
All logarithms, regardless of their base, are proportional to the natural logarithm. And the proportionality constant is d1 over the natural logarithm of the base you chose for that logarithm. And it's pretty cool to know that it makes you feel like you understand logarithms on a deeper level. I think let's take a pause here. So moving on, what we're going to talk about now is something we learned way back in elementary school, calculating percentages. And many people never really get along with calculating percentages because they never really get along with fractions, because percentage calculations are just an application of fractions. So the first thing I remember that was a huge revelation for me was someone bothering to tell me that this sign actually means something.
That sign, it simply means this each.
Good night. And as soon as I heard that, I understood percentage calculations. And I only understood it when I heard it. Otherwise, I would just sit there getting it wrong, not really understanding what I was doing. So what does it mean to write 1%? It means 1 per 100, and mathematicians write it like this, 1 for every 100. So that's exactly the same as that. What if you say it's not 1% anymore? Now it's X%.
Then it's just X out of 100.
Okay. What's 2% of 30, for example? 2% of 30, what is that? What does it mean? It just means what's 200ths of? What's 200ths of? Multiply by 30, and now you just have to know the fraction rules. You multiply a number by a fraction by multiplying the numerator, and 2 times 30, that's 60. So it's 60. Hundredths, but I can divide both the numerator and the denominator by 10, so it's 6/10. But I can divide both the numerator and the denominator by 2, so it's 3 tenths. We can't simplify it any further. And if I feel like it, I can also write it as 0.6, because 1/5 is 0.2, and I have 3 of those. 0.2 plus 0.2 plus 0.2 must be 0.6. So I can also write it as 0.6. You see, percentage calculation becomes super easy once you learn to use the rules. Then you know what you're doing.
Now here's a little sneaky detail.
Maybe you haven't thought of it, and maybe you have, in which
Can you
case,
feel
lucky
it when you see what I'm writing now?
If I take X% of,
What does that give?
Oh, well, it just means X 100ths.
And you simply have to multiply it by. And how do you multiply a number by a fraction in the numerator? So this is the same as saying X times Y. Oh, she is.
So far, so good.
What if I decide to do something completely different? Now I don't want to take X% of Y. Now I want to take Y% of X. Now I want to take Y% of X. So what is that the same as? Well, now Y is in percent, so it's only 100 parts.
And then I have to multiply X in the numerator.
But the order of factors doesn't matter, so it can be written as X times Y over 100. Because we learned in math last time that X times Y is the same as Y times X. So that always gives the same result.
And that's really cool.
Because now I've discovered that it's completely irrelevant whether we take 10% of 37.1 or 37.1% of 10. It results in the same conversation. And sometimes it's much easier to flip it when doing mental math, because 10% of 37.1, yeah, that's just the nice decimals. Then it's done. Can you see that? So that was cool, wasn't it? So we can just put that in a box. X%
Of Y is exactly the same as Y%
of X. That follows automatically from what percentage calculation is, and our calculation rules from last time.
So you can be pronounced for annoying torture tasks.
In elementary school, you're told that 7% of something you don't know gives you 13 choices you don't know. I'd like to see an example like that too. Funny.
Percent is something you don't know. You can try.
Tighten it in the red basement. Just write down what it means, then it's not so hard. Because what 7% means now is 700,000. And what the A means, it means times.
So multiply what I know as X.
And you
On
should
the
do
right
this when you're
side.
13. then there's just a plane and we're done. So if I want to get rid of 100 when it's on the bottom, I have to multiply by it. And if I want to get rid of 7 when it's on the top, I have to divide by it. So I multiply the equation by 100. So there are 7x left minus 13 times 100.
And finally, I just need to divide by 7. Then I found x.
So x is equal to 1,300.
Super cool. We don't worry about it anymore. It's just double underlined.
So if you're a physicist, you can just have this result, right? When you're a mathematician, you love it. Now it's nice, exact, precise. But if you ask a carpenter to cut a board that's 13.07 decimeters long, you'll get in trouble. So be careful with that when you become engineers. Remember to work it out as a decimal if needed, but not in math. Here, we're after understanding and insight, not the numbers themselves. Now we're ready for the 2 tasks you need to try to calculate in percentages. Mikkel and I will go around and help you. Once I've written the tasks, we'll pause the video. While you're solving them, we'll go around and help you with the camera off. And I think to be a bit kind, I'll start by writing some that are manageable, and then the 2 difficult ones will come later, right? Where it first feels like a success. So here it comes.
And toss until now.
Then you can set enough. Task 2, 2% of x. So I need to look at that. Task 2, 4.1%. Hi.
Dear,
There are 2. So there are the 3 mentioned.
And then it gets a bit harder over here. Exercise 4.
I just need to write a bit.
You've got 100 kilograms.
Applause. Containing 99.999% water. Contents. Here are the tables.
is it the right spot?
Or in stock, we can just write well lost. Well ended. That's the water content. .99998% water. How many kilos of potatoes do you have now? A lot. Potatoes. Oh, you're a nerd. We're
Just
starting.
with the 4 tasks, we'll see if there's a need for an extra one.
So if you just pause this one, how did you solve this? Now we've tried to calculate them a bit in class, so let's go over them here. The first one, it's easy. 2%, we just need to calculate from 41. So 2% of 41, that must be 200 parts. The group at 41, so I multiply 41 in the numerator and get 82. And then they are supposed to continue with.
And when you divide by 10, you move the decimal
So when you
point.
divide by 100, you move it 2 places. There's a sneaky decimal point where there's a 0, so I can just move it.
Places 0.2.
Over to you.
Does it make sense that 2% of 41 is 0.82? Yes, because if it were 2% of 100, that would be 2.
So it should be just under half.
And half of 2 is 1. And a bit under 1 is 0.82.
Remember
looks
to
like it fits pretty
sanity
well,
check your results.
When you're becoming engineers. So think, does it make
That's
sense?
the strategy
Every time he
had.
calculated, he got something from it. 10 to 18 or something with 10 to 32 or anything else.
How long should the liner be? 10 to 32 meters?
You
It
know,
could be a
as
bolt
long-
into boreholes.
So you guys are the emptiers.
Okay, 2% of something unknown should equal 18. So we can solve it like this. We just say 200 parts. Multiply x by to be equal to 18, and then I isolate x. Right? So I multiply by 100 over there, I get 1,800, and then divide by 2, so I get 900. So x must be 900. Does that sound right? If I take 2% of 100, I will get 2. Now, if I take 2% of 900, I get something that's 9 times bigger. 2 times 9 is 18. That checks out. So there's 4.1% of a number, I don't know, called y, which should give 21. So I can write that as 4.1%.
4,100 is something I don't know, which is y. And it should give 21. Then I just isolate y each time, multiplying both sides of the equation by 100. And it will be by 4.1. So y must be 21 times 100 divided by 4.1.
So that means it gives 2,100.
Over 4.1, and you can punch that into a calculator if you want. But here we're just interested in the method, so I'm just going to underline that twice. Then comes this.
Very nice, and it counts.
And it is
Sneaky.
What does it say? You have 100 kilo of potatoes with 99.999% water in them. The potatoes are now put in storage.
And that's all unaccounted in the water decatur.
'Tis bland. Not much worth eating them.
I store them. And some of the moisture.
Evaporates from them, because that's what happens if you harvest something and store it. Some of the moisture evaporates.
This is actually an issue
leaving
that's
the plant,
important in this
especially when cooking. So the water content now drops from 99.999% water to 99.9998% water. And it sounds like almost no water has disappeared. But be careful not to conclude that no water has disappeared. It turns out a lot of water has vanished. I will explain intuitively why it must be so shortly. But what we can do is solve the problem by thinking before and after. What do we know before drying, and what do we know after?
So try to do that over here.
Yeah.
To tackle this, we know the following.
We know that we have 99.999 kilograms of water.
That's how much water is in the potatoes before we dry them. Why? Well, because there was 99.999% water. And if that's by mass percentage, then it must be 99.9999 kilograms of water. But if there are 100 kilograms of potatoes, and some is water and some is not, how much is not water before we dry? It must be the remainder up to 100 indeed. So it's 0.001. So we have 0.001 kilograms of dry matter before we start drying the potatoes by storing them. So that's what we know beforehand.
Let's show the follow-up.
And yeah, this way of thinking when solving these problems almost always works. What do I know before? What do I know after? Write it down. What can I say? Solve it. And the cool thing about math is, the more math you've learned, the less stuff you need to know to answer correctly. You just set up the math like bam, 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 done. You can trust that. So what do we know after?
Well, we know that
Still
we
have 0.001 kilograms of dry
Because it
matter
hasn't disappeared just because the water
evaporated.
So we still have 0.001.
Kilograms of dry matter. We know we still have that.
See, you made it together.
What we also know is that we have 99.
Coming 9.
9.8% water.
But we don't know how many kilograms of potatoes we have. We don't know that. We just know that no matter how many we have, 99.998% of it is water. Well, if 99.998% of it is water, how many percent isn't water? It has to be the rest up to 100%. So that means I also have 0.002% water, percent of the number of kilos of potatoes I have,
which I don't know, so I'll call it x. So the rest of the percentages up to 100 taken from the number of kilos of potatoes should give me my dry matter. Because what isn't water is dry matter. And this is water, but then it must be dry matter. So this must equal the dry matter I have, which I'm now going to reach.
It's a source of power.
And then it's just about solving that equation. And we've set up an equation. So what does percent mean now per 100? So 0.002% means 0.002 hundredths.
Thanks for watching.
Something I don't know,
Which is the number of kilograms of potatoes after drying.
cut in 0.001.
So you're not having a hard time starting with 100.
And I want to with 0.002. So here comes an implication arrow. X equals 0.01 times 100. Literally, it's necessary.
0.02.
What does it say here? It says what is half
Of 100. You just forget all the needles. And half of 100 is 50. So the correct answer is 50 kilograms of potatoes.
And then mathematicians do like this when there's something they're really surprised by. What? 50? That must be wrong, you think? But it's correct. It is indeed 50. And once you truly understand intuitively why, you'll realize that even if I had said 99 billion, 999 million, 999,000, 999.809 million, 999,999, and then change the last one to 8, it would still be 50. So it's simply that we can understand why intuitively. And I usually think of it like this. If this square
Speed represents the potatoes.
before I start drying them, it's all water anyway. We can almost say it's all water. H2. Then there's a bit of
A tiny
solid
bit of dry matter up here in the corner. So it's a bit of dry matter.
Now look here. If 99.999% is water, and there's a tiny bit of dry matter, 0.001% dry matter here. So what happens if I remove half of the water? Remove all this, it's gone. Can you see that it's still all water? All this water is a tiny bit of dry matter. So I can remove half of the water and it has hardly changed the percentage that the water constitutes. Because it was almost all water to start with and it's almost all water afterward as well. And that's why I can actually remove half of the water and it practically doesn't change the percentage of water in the potatoes. And that's why sometimes the percentage takes 1000 points. And that's why I think you should see that task. It's because sometimes it can give counterintuitive results.
But once you get it framed correctly in your mind, it suddenly makes sense again.
Okay, let's take a 10-minute break. And then there will be another task on percentage calculation. And afterwards, I'll start with function theory. Okay, here's another example where you can apply percentage calculation. I thought about giving it to you in class, but I'll spare you and just explain how it's done. Imagine the following story. A man and a woman are out to buy an ice cream cone.
Here I've tried to draw the ice cream cone in perspective. It's like a cone. And this cone has some height, from here to here.
And it has some opening radius, this cone from here to here, which I call R. And in school mathematics, you learn that the volume is such a cone there. It can be found as 1/3 times radius squared times pi and then times height. That's how you find the volume of a cone. And imagine now that this man and his wife drive out to get an ice cream. And the ice cream is filled right to the top of the cone. And no more, because the people who make ice cream there are kind of stingy, right?
And they can only afford one ice cream, so they have to share. Well, let's just see some sort of reason for
And
the
then I
bill.
play steadily.
So the question is, what percentage is it?
He's the ice cream box.
So eat an elderberry
Found
shark.
Half the ice cream.
And I'd like to hear a few guesses before I show you how to figure it out. So does anyone have an idea of what percentage of the height he should eat? Is it 10% of the height or is it 50% of the height? How much of the height should he eat before he's eaten half the ice cream? What do you think?
See you tomorrow.
Should I forget it?
Yes. Okay. Yeah. About 25%. Yes. Any other guesses?
20 and 20.
Okay. Yes. Other bid.
Hello? 50%? Don't you think there's more ice cream up here at the top? If he eats 50% here, then there's just a tiny innocent bit of ice cream left for her. Basically no ice cream, right? You can see there's a lot of ice cream up here at the top, so it can hardly be 50%, can it?
Yes, it's 50% of the height we lived at here.
15%. Okay. Yes, yes.
How much? 1%? Okay, well then let's try to calculate it.
If you know someone who's good at math, try giving this to them. It's not everyone who's good at math who can even solve it either, because you really need to think it through. But there's an easy way to think about it, which looks like this. Down here, there's an angle to that ice cream cone. And when you eat from the top of the ice cream cone, it doesn't change the angle.
Well, we'll see that
When
next
it's eaten.
week. The ice cream looks like this.
I've got a slightly smaller ice cream, but it has the same angle down here. I actually didn't draw the angle to include it, but that's what I meant. And here is the ice after the man has eaten, and now it has reached a new height here, and it has a new angle. Opening radius here.
And the question is, how should I write it then?
You probably remember that if you have a certain amount of money and want to add VAT, then you multiply by
1.25. So if you have 100 krona and want to add fatty, you multiply by 1.25.
What if you want to take 20% off? What do you multiply by? 0.8. So you can see you can make something smaller by scaling it with a value between
Numbers between 0 and 1.
So if you imagine you have a scaling constant, we'll call it k. We know that since you become less when the man starts eating, it must lie between 0 and 1. Can you imagine that? If you multiply something by a number between 0 and 1, it becomes smaller. It becomes a certain percent smaller. If you multiply by 0.8, it's 20% smaller. Multiply by 0.7, it's 30% smaller. Are you following? So imagine the new height. I got it by taking some unknown scaling constant and multiplying it by the old height.
And I know that this k is between 0 and 1.
But now you can imagine if this angle here doesn't change. So the same scaling constant the man needs to learn the height with, because he eats the ice cream, he also has to learn the radius with. Because it's the ice cream that's left. It becomes smaller and smaller in radius. So the new radius becomes the same scaling constant times r. And what we know is that this is the volume of the ice cream before the man eats. What's the volume of the ice cream after? After the man eats? It should be half, that's what we've been told. So it must be half of what it was to start with.
And how much was it to start with? That there.
So half is 1/3 times radius squared times p times height. But that ice cream, after the man has eaten, it has a volume that we can use the same formula to calculate. We just need to use the new radius and the new height. So what we also know is that this is also equal to the same formula applied again. That is 1/3 times radius squared times pi times h. But now I just need to use the new radius. So now I have to write it like this. Here's the new radius, and it must be squared and multiplied by pi. And it must be multiplied by the new height, but it's k times the old height. Can you see there?
So what I know is this must equal that.
I'll just write it down. So I get that half times 1/3 times radius squared times pi times the height. That should be equal to 1/3 times this. And that is k squared, r squared. I'll put the r squared first. Then comes pi. Then comes the head. And finally, you can see it says k times k squared. That gives k cubed. Thank you. And now a whole bunch of things cancel out and we're done with the tasks. Take a look here.
Third consonant with third.
And r times p times h, it cancels out with r times p times h if I divide by it. So what's left is that half is equal to k cubed.
So I should be able to find k. Now I know how much the ice has escalated.
I just need to isolate k. And how do I get rid of a cubed exponent? I take the cube root. Notice I don't need to use logarithms, because here I need to find the base, not the exponent. Logarithms are for finding exponents. Here I need to find the base, so I have to use roots. I take the cube root on both sides, so the scaling constant becomes the cube root of 1/2. And that's the same as taking the cube root of the numerator, called the cube root of the denominator. The cube root of 1 is 1 itself. And then over the cube root of 2. And here's the answer, basically. If that gives 0.8, then the person has to eat 20%. If that gives 0.7, then he has to eat 30%. So how does my final answer look? Well, what's the percentage? Try thinking about it again. If that number is 0.8, then he has to eat 20%. When do I go from 0.8 to 20%? I say 1 minus 0.8 and then multiply by 100, and then I have the percentage. Can you see that? So I have to say 1 minus this number here, and then I multiply by 100, and then I have it in percent. So it gives 1 minus 1 over the cube root of 2. All that times 100, and then I have that project. And then you can, if you find it interesting, just punch it into a calculator. I can't remember numbers, so I just have to enter it. Then we get a sense if it makes sense, you know, with our sanity check. So I just say
1 divided by 2 raised to the power of 1/3.
And then I say 1 minus that, and then I multiply by 100. And then I get it to 20.63. See you there. So the man must eat 20.63% of the ice cream's height to have eaten half. If she's a bit meticulous, she can measure the height of the ice cream first. And then we'll find out how much he's eaten by standing on board and marking a line. Done. And this is also an example of percentage calculations, but it's not very easy percentage calculations because you have to start thinking about escalations and stuff like that first. So we need to know the top and all that stuff. So that's why in math problems, we assume all sorts of things that never match reality, but then we can at least calculate it. All right, do you have any questions? That's because the entire ice cream scales the same way when you eat from the top. The angle at the bottom doesn't change. That means you can imagine that this ice cream is identical to that ice cream, but just in a universe that's shrunk, and all the dimensions in the universe have shrunk at the same rate. So the radius has to shrink at the same rate as the height. Okay, so you just did this to the universe, made it smaller. It came from here because here it says kr all squared, which means it gives a third k year, r year, I, k, r year. And could multiply, could help.
GTK and 30, yes.
A task that's a bit similar is two boys spending Christmas at their grandma and grandpa's, and there's a bowl of tangerines. These are the tangerines. And then all of a sudden, there's a tangerine that's twice the diameter. And the big brother gets there first, so of course he takes the biggest one. He picks a mandarin with a diameter twice as large as all the others, which we assume are the same. And the question is, how many mandarins does the little brother need to eat? Because he got just as much mandarin. Does anyone have a guess on that? How many mandarins do you have to eat to get the same amount as the big brother if he took one with a double diameter? What 4 is a guess, right? 3.14, that's also a guess. It would be kind of magical if it was P. I got chills and thought. But here, you have to get how to find the volume of a sphere, because the volume is a sphere. It's 4/3, pi to the third power. You can look it up in a formula collection if you don't remember it. What does that tell us? If the radius is 1, what does 1 cubed give? Because 1 times 1 is 1. What if the radius is double that? Because the big brother picked one that was twice as big. What is 2 cubed? 2 times 2 times 2 is 8. So the volume is 8 times larger if you double the radius. So the little brother has to eat 8. And guess who ended up looking like porridge? It was the little brother. He just didn't take any more than the big brother. So sometimes you're surprised by those scaling laws, that a sphere grows much faster in volume. lightning fast if you change the radius. So try thinking about how big a sphere we live on.
Because the Earth's radius is 6,371,000 meters.
So we live on a giant ball.
And because it's so huge, there are some people who go around thinking it's flat. The Earth is actually flat as a first order linear approximation to reality when you're close to it.
But those who think it's flat didn't know any of these words.
Okay, let's jump right into reviewing some stuff about functions. So I'll wipe the board and then we'll start reviewing functions. You had this in Math B and Math A, but we need to be on top of the essential functions before we tackle Pentium. And as I said, just ask questions along the way if there's suddenly something you can't remember or want explained in more detail.
The heading is now function storage.
In math, we talk about functions. And what is a function? A function is something that takes an input, does something to it, and sends an output out the other end. We usually draw a little diagram where we show here's the input, which I throw into a function machine. So I'll draw a box to show it's a machine. Inside, something happens to x, and out comes a new number, which is typically called y. The number x here is free to take on any value it wants to. That's why you call that variable independent.
You have the freedom to choose what value it wants to be. So we call that the independent variable.
What comes out of the machine depends on what we put in. So that's why it's called the dependent variable. The rule that tells us what happens to x to create our y, we call the function's formula. And we write something like fx to indicate there's a function f that is eager to get an x to operate on, so we can generate a y.
And when f has worked on x, y comes out.
It must be such that for every chosen value of x, there corresponds one and only one y. We can't have two y's come out. We can't have a schizophrenic machine. That's not acceptable. We can't have a machine saying if you put in an x, it can't really decide what should come out. That's not a function. A graph of such a function, if it existed, would look like this. It's one that can't make up its mind. So that there, that's not a graph.
Watch as I draw this in a coordinate system.
And I choose an x here and have a schizophrenic function. So it does this. Should it be u, or should it be u, or should it be u coming out? That's not acceptable. That's not a function. Does this mean mathematicians can never describe something that looks like this?
No, it doesn't. You just need to use the vector function.
But it's not a graph. It's a path curve for a vector function.
So when dealing with functions, the graphs look more like this. They can't have vertical tangents. Are there vertical tangents here? Yes, there's a vertical one there.
And then maybe a gradient here.
And maybe one there.
So a graph, no matter what, it could look like this.
If you draw the relationship between the x's and the y's, where you have an x-axis here, and perpendicular to it you have a y-axis, you have what's called the Cartesian coordinate system. And if you draw the relationship between the x's and the y's in that, you get what's called the graph. And it could look like this, for example. It should look like this. It just mustn't become tangled, and it mustn't loop around and intersect itself. Then it's not a graph, but a function anymore. Over. Now, some names have been invented that you just need to know. The number of x's that you can put into the function machine, they go from here to here on my drawing. Can you see it? From here to here. That's called the domain of the function. And you write DOM to abbreviate domain. So what's that? It's the set of valid x's. It's a set
The set of valid x values.
if you look at the y-axis, we go from here to up here. The other y values on my drawing, that's the range of possible y values. And that's called the range where you write R, D, and I. And R, D, and I mean the range of possible y values what's this chain they've made? It happens all the time. So a function is something that can be drawn in a coordinate system. It becomes a graph. The graph shows the relationship between x and y. And a function has a domain and a range. Let's take an example of a function. What could a function look like? It could look like this, for example. Example 1, f of x equals x squared. That's a function. It's hungry for an x to work on, so it can generate a y. Now, if you, for instance, feed it with a 1, you write it like this. What do you give if I feed you a 1? And then it says, I give what you get if you put 1 in place of x in the function machine. So I just need to put my 1 right there. Then it stands as 1 squared, which is 1 itself. So this is my input. That was x. Here's my output. That's y. Every time f works on an input, an output comes out. If I then ask f, what do you give if I put 2 in? It says, I give 2 squared. Now you need to put 2 in place of x, and that gives 4. If I ask, what do you give if I put fedipole in place of x? You need to be careful, because if I say f, it's fedipole, or R9. Then the function takes fedipole and squares it. And don't be offended. It just says f times e times d times e times p times a times u times l. That's what's written here.
But it's definitely that number that needs to be put in.
What happens if I plug in x0 plus h? Well, what does f of x0 plus h give you? Now, these are just two numbers that I won't reveal. So I'll call one x0 and the other h. There's a good reason for choosing them, because when we learn to differentiate, you'll see why. So I just need to take x0 plus h and substitute it in x's place, and then put h in its place. So a function is something that does something to an input and generates an output. And the relationship between input and output can be drawn, and the drawing is called a graph. So far, so good. Now let's review the most commonly used functions in mathematical analysis that you had at B level and A level.
If no one has any questions, let's wipe the board.
Okay. There's a function we usually call a linear function.
And you had that once at C level, I think.
To be precise, you need to distinguish between similar functions and those functions by strictly defined application. You need to distinguish between the two things. The similar functions all go through Oreco. So the similar function looks like this. Y equals ax. Done. Finished. Something like that. So this is the similar function, and a is the slope coefficient. So if you draw the graph, it looks like this, for example. It goes straight through the origin and has a slope of a. It means pick any point, give x an increment of exactly 1. Now you will change exactly by. This is also called a proportionality law, and you say y is proportional to x because you can find y by taking an appropriate number, which is a constant, and multiply it by x. So y is proportional to x, and that gives linear functions. So there are all these functions. If the graph becomes a straight line, they are strictly speaking not linear functions unless b and 0, but that's unfortunately how they are called in high school. But this function here, f of x equals a x plus b. These are the types of functions whose graphs become a straight line, but they are only linear if b is 0, because if you want a similar mapping, the 0 vector must map to the 0 vector. We'll get to that in linear algebra. You're very familiar with this type of function. The graph looks like this. It's the range of functions whose graph becomes a straight line. So here is an example of such a function. The point where it intersects the y-axis, that's b. Why? Well, see, if I let f act on 0, what do I get? It becomes 0. Sorry, a times 0 plus b, and a times 0 plus b simply gives b itself. So we can see the y value becomes b when x is 0. Here, when x is 0, the y value becomes b. The slope coefficient means choosing a random point to increase x by exactly 1 in the positive x direction. The change in y will now be due to the slope, and here we need 90 degrees. So that's the slope coefficient, the intersection with the y-axis. If you want to find the equation of a straight line that goes through two known points, you do it like this. Here I have a coordinate system, and now I have two known points. I call one point P1, the other P2. Here's x1. Here's x2. And here is y1. And here is y2. How many straight lines pass through the point P1? Infinitely many. Namely, all those infinite straight lines that pass through P1 and can rotate around P1.
How many straight lines pass through both P1 and P2?
Exactly one. One and only one. So any straight line is uniquely determined if I know two different points it must pass through. Therefore, there must be an equation for the unique straight line that passes through P1 and P2, and I can name it lone. So there's an L for lone. Lone passes through P1 and P2. But what is lone's equation? Lone is a set of functions whose graph forms a straight line, and lone is a straight line, so it looks like this. And if you need to find the slope of, you just have to remember that the slope means how much y changes every time you change x by some amount. And if we draw here, we can see that we can create a triangle that shows how much x has changed. It has changed from here to there. And up here we can see how much further it reaches. So that means y has changed by asking what was the y coordinate of P2 minus what was the y coordinate of P1, and then divide by the corresponding things on x. And now we have the solution.
So this is how you find the slope of a straight line.
And you know that y equals x plus b. So how do you find b? Well, you know that if you insert x1, it should give you y1. So you can just put a 1 there and there and isolate b. And then we're done. So b can be found like this.
As y1 minus x1.
But we also know that besides point P1 being on the line, P2 is also on the line. So you could also choose to write a total there and a total there. So this would be the same as if I just wrote U2 minus AX2. So you can choose yourself whether you find B like this or like that. It's your choice. That was a strange line. So I want to repeat for you something called the polynomial of regret. We will need it. Ouch. Let's make a heading. Second degree.
Holy, no miedo.
Which is still true. I think it's a limit on your surroundings. Wholly means many. So that means a polynomial is something with many terms. A monomile is something with only one. And mono means one. So this is a monomile. This is a monomial.
This is also a monomial.
But it is a polynomial, and it's actually a third degree polynomial. And now there is something called a second degree polynomial, which is when the highest exponent on x is 2. So a second degree polynomial looks like this: some number times x raised to the power of 2, plus some number times x raised to the power of 1 plus some number c times x raised to the power of 0. And this is my function, so I can write f of x equals that. If this structure is there, you call it a second degree polynomial.
But we learned in algebra that x to the power of 0 equals 1. And that's why we never write it. So get rid of that.
And we've also learned that x to the power of 1 is x itself. So that's why we never write that. But you could see that the structure was 2, 1, 0. So these are decreasing exponents on x. Then you have a second degree polynomial.
It turned out that the graph changed.
A second degree polynomial becomes a shape that we call a parabola. If I just draw one like this. So maybe I had a parabola that looked like this. That's roughly the shape a rope has. If you take a rope and cut it so that it's too long to reach between your hands, it'll hang down here. And the shape it hangs in is close to being a parabola. Not exactly, but pretty close. If I throw this off, it travels in an arc path, which, if I ignore air resistance, is a perfect parabola. If you were in a completely perfect homogeneous gravitational field, which we aren't, but it's close, it becomes very close to a parabola if we throw an object heavy enough that air resistance can be ignored. This one doesn't intersect the x-axis at all. So does it have a discriminant greater than 0, less than 0, equal to 0? What do you say? Less than 0? Yes. So here I could write this one on a board. It definitely has discriminant less than 0. Now I have another parabola here. It intersects the x-axis in two places. So what discriminant does it have? Greater than 0. So here's an example of a parabola with a discriminant greater than 0. And lastly, you could have a parabola that looks like a real kiss. The x-axis is just one point. You call that a vertex. Whether it's at the top or bottom, you call it a vertex. And here, the discriminant will be exactly 0.
So this one has a discriminant of 0.
If you want to know the coordinates of the vertex, let's say this point is t for the vertex, and I want to know the x-coordinate and the y-coordinate of the vertex, then there's a formula that looks like this. The x-coordinate of the vertex is b over 2a. And the y-coordinate of the vertex is d over 4a. If you need to solve a quadratic equation, what is it? A quadratic equation is the equation you get when you ask facts. When do you give 0? So a fact says, I give 0 when what I'm equal to gives a 0. So that means if ax squared plus bx plus c is equal to 0, you have a quadratic equation. It looks like this. X squared plus bx plus c equals 0.
X plus c
Equals 0. This is called a quadratic equation.
And it can be solved.
With the method that will appear on the next board. And once I've written it down, I think we'll take a break. Are there any questions about the board before we erase it?
Yes, it's because the peak is at the same spot as the place where it needs to exit the x-axis if it's going to leave the x-axis. So if you have a different boundary line, meaning a line that looks like this, then you can solve it by using some of the math we learned last time. And here it comes. You multiply the straight line through by 4a. Why? It has turned out to be a good idea. Someone thought of it and discovered that this way you can make a smart rewriting. So it wasn't me who came up with it. Somebody thought of it, and I'm just following them. I multiply the whole line through by 4a. So I get 4a times that. It must give this. So it's already got an a beforehand. Then I multiply that by 4a. It must give this. Then I multiply it by 4a. And then I multiply 0 by 4a. But 0 times anything is still 0. So I find it annoying that there's no x on it when there is on that one and that one. So the part that has nothing to do with x, I think should be kept aside a bit. So I toss it outside the door, over on the other side of the design. So now it says 4a squared, x squared. Plus 4abx, it's with minus 4ac. And then I remember that I once taught you something called the discriminant. It was something with b squared minus 4ac. It looks like what's there, it's just missing b squared. So I get the good idea to add b squared to both sides of the equation sign. So I just add b squared to both sides of the equation sign. Why? Because I can, and it's a good idea. So I get 4x plus 4abx plus the b, because I add the b to the left side, but I also have to do it on the right side. So it becomes b minus 4ac. Then I look at the left side and say, hey, this can be rewritten into something smart. All of this, it can actually be rewritten to what I'm now writing and explain 2ax plus b, all of its squares. Try to see for yourself. It's the square of a two-dimensional value. If I calculate it, the first term squared is what it gives. 4x squared, that's what you get if you square that. B squared, that's there. The double product, it's back then. Then the lucky total is there. On the right side, I don't think it looks so nice anymore. So I call all of this D. It's just a number. It's actually the number you get if you know A, B, and C and calculate this, then you get D. And now, of course, there are three possibilities for that number. It can turn out to be positive or negative or 0. I don't know what it gives because it's purely abstract thinking. So I just assume something. Let's assume it's positive. If it's positive, then there is, can you just find me a number that signifies D? How many numbers are there that signify D if D is positive? How many numbers are there that signify 25, 5, and negative 5? So there are two numbers. That means I now have that 2ax plus b squared. If it equals D, then the solution must be either plus or minus the square root of D. So I just take the square root on both sides and say that 2ax plus b must be equal to either the positive or negative square root of D. Now I can isolate x. I just subtract b and divide by 2a. So I found x. So x equals negative b plus or minus the square root of D. All of this taken over. And that's how you solve a quadratic equation if the discriminant is positive. But it's not certain that it's positive. What if it's 0? Well, then we just assume that too and think it's done. If it's 0, then it says, can't you find me a number that is marked 0? The only number that is marked 0 is 0 itself. So I conclude that the expression 2ax plus b must equal 0. But this can only be 0 if x is minus b divided by 2a. So I isolate x by subtracting b and dividing by 2a. So x is minus b over 2a, and that's how you solve a quadratic equation if the discriminant is 0.
Then, of course, there's also the possibility that the discriminant is negative. So then it's like this. It has to be just like this.
Error reached a solution. Before a bit later, about a month's time, then it's again. And then we start with complex numbers, or we are well underway with complex numbers, and then you can still solve it. But so far, there is no solution, so the solution set is empty. As long as it only looks for solutions in the real number space, where plain old good numbers are found. What kind of numbers are these? The number of apples, for example. It's also the number of apples you owe if you've eaten someone else's apples. These are also real numbers. It's also if you take an apple and cut it in half. We call this a rational number. It becomes a ratio. It becomes a fraction. It's also the number of square root of 2, which is the side length in a right angle triangle, where the two legs are both on one long side. That's also a real number. It's also p, which is the ratio of a circle's circumference to its diameter. Then there's finally a real number, which is the square root of minus 1. That's not a real number. It's the imaginary unit.
Which remains noteworthy. And the amazing thing is, it appears in physics, in quantum mechanics, and in wave equations.
So if one solves the smoke, the ghost issue, one ends up at least within alignment in a Hilbert space of complex numbers, then you get the probability of finding a particle in the real world. No, it's not strange. It's really quite odd though. But complex numbers can be used for all sorts of things, even though they made them up.
I think it's time to take a break. I feel like I need a peach. So let's just take a 10-minute break if you're up for it.
So if you have an equation like that, you can solve it with that formula if the discriminant is positive, and that formula if the discriminant is 0. But you don't always need to use that formula or that formula. Sometimes you can solve it directly, like you saw in the first test we had. So if you now have an equation that looks like this, x minus 1 times x plus 1 equals 0. So it's a different equation. How can I see that? Well, because if I multiply this one by that one, and this one by that one, if I multiply this one by that one, I get x squared. And this one by that one, I get plus x. And this one by that one, I get minus x. And this one by that one, I get minus 1. So we can see that it's an equation because we can combine the two to get 0. So basically, it just says x squared minus 1 equals 0. So you can rewrite that equation to this and then start using this formula by identifying A, B, and C. And A is an implied one there, and B must be 0 because there are no x terms, you see. And C, it must be minus 1, and then you can insert it into the formula, and then the solution comes. But that would just be silly because we were so lucky that the task from the start was in what is called factored form. And then you can solve with the zero product rule. So if you just look at this up here, you just have to write like this to the examiner. Dear examiner, I am using the zero product rule. And it tells me that either this must be 0 or this must be 0, because a product of two numbers can only be 0 if at least one of the numbers is 0. And that means either x has to be 1. Oops, 1. Or x has to be minus 1. And you would also get that if you use that formula and then read off A, B, and C and went ahead with the discriminant and all that. So we can just try to show an example where you are forced to use the method with the discriminant. That means almost forced. Example 2. If now I have an equation that is 1x squared plus 1x minus 6 equals 0. It is another quadratic equation. A is 1, B is 1, C is minus 6. So we can just write that A is 1, B is 1, C is minus 6. So I can calculate the discriminant. It was b squared minus 4ac. So I plug in the numbers. B squared, that's 1 squared. It's 1 minus 4 times 1, because A was 1, times C, which is minus 6. Minus times minus is plus, and 4 times 6 is 24. So it's 1 plus 24, which is 25. And since 25 is a number greater than 0, I can use this solution formula I've written up here. So since this is greater than 0, it means there are two solutions. And I can find them by using the proposed solution.
The formula written there. So what is x?
It's minus b plus or minus the square root of d over 2 times a. And then we plug in the numbers. So minus b must be minus 1 plus or minus the square root of 25, which gives 5. And the whole thing is divided by 2 times a, but a was 1. So that gives 2. Minus 1 plus 5 is 4 over 2, which is 2. So one solution is 2. Minus 1 minus 5 is minus 6 over 2, which is minus 3. And here are the two solutions.
So we just reviewed how to solve other types of lines.
Now we need to look a bit at what's called exponential developments. It's also quite nice to have that refreshed.
Does anyone have any questions about the board?
Yeah, so I'll start by picking up over here first.
And don't worry, when we reach new material, I'll be sure to slow down.
It's just that I think I get boring to listen to quickly over.
That's good.
It's maybe quite nice to see it right here as we're going through it. I said, since it's a product between two numbers that needs to equal 0, I could just use the 0 rule and say either one factor has to be 0 or the other has to be 0. What does x have to be for that to equal 0? What does x have to be for this to equal 0? -1, and then we're done. I must stay hidden. Okay. There's another class of functions that's important to know called exponential developments. And now, not everyone is equally fond of math. Some like it less than others. I have a funny story about exponential growth. Back when I was in high school, my dad was taking adult education courses and studying math at the B level and then later at the A level. I was taking math at the same time, so we could chat about it, which was quite nice. And the people my dad was studying math with weren't all big fans of it either. I remember going down to his school to find out how he'd done after a monthly math exam at the B level. There was a girl standing outside the door looking really upset. And then my dad asked her, how did it go? Not so well, she said. I pulled exponential growth. She hadn't quite gotten the name right. It should be exponential. We looked at each other and had to step aside because that was awkward. But it's called exponential because it deals with exponents. And exponential growth looks like this. F of x equals some number b times some number a raised to the power of x. We usually limit it so that the number b is positive. So you'd write to your neighbor, indicating that b can be freely chosen from the set of positive real numbers. And that number a, we also usually say is positive. But what we distinguish between is whether a falls between 0 and 1, therefore positive, or is greater than 1. We'll see why in a bit. Because it turns out if a is greater than 1, you can imagine if, say, 10, which is greater than 1, the larger x becomes, the larger a raised to the power of x becomes. Because 10 squared is less than 10 cubed. So as x grows, a to the power of x will also grow if a is a number greater than 1. A is called the growth factor. And if you have a number a that is greater than 1, this is how the graph will look like this out to the heart. It will be adults. And then I say something like this. And it grows exponentially, meaning the growth rate increases as x gets larger. So the further you go out here, the faster it ascends. And the place where it intersects the y-axis, you can figure that out just by asking, what does f of 0 give? So if I set x to 0 here in the function, it says b times a to the 0. But since a to the 0 was defined in the last lecture to be 1, it just gives b, where b times 1, which is just b. So this is called the initial value for an exponential function. If it's physics, the clock starts here. If it's time out along the x-axis, then it proceeds exponentially. And if you have a function that grows like this one does and follows this pattern, it has what's called a doubling constant. And that means if I have b here, I can say I want to have b. At an x value of 0, how much does x need to become for me to double b to reach 2b? So the x value out here is called the doubling constant x2. We can find a formula for it. We know that 2b is what comes out of the function machine if x2 is inserted in place of x. So I get that 2b comes out of the machine if I put x2 in place of x in the machine. We can see that we can divide the b away
So what we now have is that 2 equals a raised to the power of x2. And if we want to find an exponent, we need an exponent finder, which is a logarithm. So I take the natural logarithm on both sides, assuming I only have a calculator with a natural logarithm button.
So it will say the natural log of 2
is equal to the natural log of a raised to the power of x2. We can use one of the rules we learned last time, where you can multiply the exponent in front here. That was logarithm rule 3 from last time. So now I get that x2 times ln a alone with ln 2. If I just swap the right and left side, and then I can finally divide by ln a, and then I have a formula. So the doubling constant for an exponentially growing process is the natural logarithm of the number 2. That is with the natural logarithm of the growth factor a. If on the other hand, a is not greater than 1, if now that a is between 0 and 1, then the situation looks completely different. So if a is between 0 and 1, then the situation looks completely different.
So you can probably imagine what
that number is
happens.
between 0 and 1, for example, 1/2. What happens when you take 1/2 and multiply it by itself a certain number of times? Well, the result gets smaller and smaller the more times you multiply it by itself. 1/2 times 1/2 is 1/4, times 1/2 is 1/8, and so on. So that's why you now get what's called an exponentially decreasing function. And it would look something like this. And asymptotically, it approaches 0. It never touches the x-axis, but it gets very close. And the place where it hits the y-axis is still b, for the same reason as before, because f of 0 is still b, even though a is now between 0 and 1. And something like this has a half-life constant. Now imagine you want to halve b and get it down to half of b, and then you ask what exact value you would want.
to it.
Well, that's the x value, x and half. And from there, you can derive, just like we just did, no point in doing it again, a formula that looks like this. The half-life constant is minus the natural logarithm of 2 divided by the logarithm of the growth factor. And I believe some people might call it this, the depreciation factor. We're going downhill. That was a bit about exponential growth. You could say a bit more, like what x values you can put in there. Anything. So, the domain.
For this function fx, it's all real numbers.
But note that when you look at the graph, regardless of whether it goes this way or that way, it stays entirely above the x-axis. Nothing goes below the x-axis. So the only y values that can come out are all positive. So the range for exponential growths is all positive real numbers. And the last thing I'll mention on this board is, how do you differentiate?
And then you find f prime x.
Well, this is how you do it. You keep the constant b, it's in action, so it stays as it is.
And the AEXs are differentiated.
Now, some of you might be thinking it's not just about multiplying it down in front and subtracting 1.
That's wrong, because this is an exponential function. So that's incorrect.
The texts are differentiated. That's obvious. It's almost obvious you need to remember to multiply with the natural logarithm of the base number. That's how you differentiate. If anyone is interested in seeing the proof, we can wrap up with a break, but that's how it's done. Okay, the next thing I need to talk about is something many people never quite become friends with, which is unit circles. So let's give it another try to become friends with unit circles here on a Friday, when we're tired, sweating, and there's no ventilation and all that, right? So let's try to take a look at the unit circle. And after I've talked about it and how you can use it with right triangles, I'll put up some exercises. Then you're free to go. But if you'd rather stay here and sweat it out, you can start solving them right away. If you say you want to go home, enjoy the weekend, and have a cold one or something, you're welcome to do that. Does anyone have any questions about the board here? Okay, so the unit circle.
And the trigonometric functions.
I'm already regretting starting the radar one now. 3, 2, 1.
3 must functions.
What we're imagining now is a guy with a Stratos.
Though it doesn't quite fit.
Blowing paint into the universe.
And then he gets to stand there with it at the same time.
Meanwhile, there's another guy who, of course, runs by with an infinitely long piece of paper,
Runs past the shovel head.
and while he's with the other, he's standing down there with the spray can. And the other runs past with a piece of paper, so they've drawn a path curve on that piece of paper.
That curve is called a sine function.
Or
It tasted
it looks
better.
a little different from cosine because it's the same main form
It just depends on when he starts pressing the nozzle.
in relation to where the guy got to.
So let's just explain where these graphs come from.
From that spot, imagine a circle. If you imagine it as a circle, you draw it with its center at the origin of a coordinate system. And then you keep an eye on a point that moves around on this circle, and the circle has a radius of 1.
So this
The radius
here,
is 1, and here's a point we're watching. It could, for example, be a valve on a bicycle wheel. And the bicycle wheel has a radius of 1 meter. So it's a huge bicycle wheel. And what I want you to imagine now is that there's an angle between a spoke on the wheel and some reference line. I call that angle V for angle. Isn't it clear now that this point here, P, has an x coordinate, and that x coordinate, xp, obviously depends on the angle. Because if the angle changes, then P moves, and P gets a new x coordinate. So it must be clear to everyone that the x coordinate of point P depends on the angle V. And that's what we call a function. And the way it depends on the angle has been given a name, and the name became cosine because it had to be something.
So there's nothing to understand here. The customers accept it. Cosine means by definition.
What is the x coordinate of a point on a circle with radius 1 and center Eurico? What is the x coordinate of a point on a circle with radius 1 and center Eurico? At that point, that's what cosine means. The x coordinate of a point on a circle with center at the moment over radius 1, depending on the size of the angle from the x-axis to the line connecting the moment to that point. And the way it depends on that angle, we give it a name, and the name is cosine. So this is more about accepting than understanding, really. But what you need to understand is that if point P starts moving, the angle changes, and so does the x-coordinate. So when point P starts moving around the circle, what's the largest the x-coordinate can be? We know that when we're here at home. Then the x-coordinate is 1. So the largest the x-coordinate can be is 1, and the smallest it can give is -1, +1, -1, +1, and that continues infinitely. And we can scrape it like this, right in between, well, not exactly in between, but somewhere between -1.
And 1 adding cosine to an arbitrary angle.
And similarly, point P has a y-coordinate that is located here. And that y-coordinate clearly depends on these angles here, because if the angle changes, P moves, and if P moves, then P's y-coordinate changes.
The way the y-coordinate depends on the angle has been given the name sine. So here is the y-coordinate for P.
And the coordinate for P depends on V. And this dependency has been named sine. And just like with cosine, you can probably see from my drawing that the largest y-coordinate it can give is +1, and the smallest it can give is -1.
So just like with cosine, sine is related to the angle
between plus and -1. If you then zoom in on this triangle, which looks like this, and draw it again down here, you can imagine there's 1 here, And then we have a right triangle here, where here is the cosine of phi. And here is the sine of phi. And there was an ancient Greek mathematician who told us how the sides relate to each other in a right triangle, namely the 1 squared plus the other squared equals the last 1 squared. That means we get a scene. And it has been decided that you are allowed to write in 2D, seen on the other side of that angle. Remember, with us, squared to the same angle, it's always 1 squared, but 1 squared is just 1. And this we call in Denmark the idiot formula. So you can use it to deduce where you are if you forget the formula. But actually, it's just called the basic relation if you look it up in a mathematics book for the unit circle. And now you can imagine if you have a triangle where there's not a 1 here in the hypotenuse, but a 7. So it's just in a universe 7 times larger. It's just scaled up by a factor of 7. So this side is no longer sine of the angle. It's 7 times more than sine of the angle. And this one is no longer cosine. It is 7 times longer than cosine. Can you see that? So if I have a triangle that looks like this, where it's not 1 long here, now it's h long, and h stands for hypotenuse.
It's hybrid.
The hypotenuse is the name for the longest side in a right triangle. I mean, so by no longer the sine, it will be h times more than sine, because we've scaled by a factor of h.
And here will be h times cosine.
And that's something the engineers can use. Because now you're dealing with a triangle where you know this angle down here. So you always know that the side adjacent to the angle is a factor of cosine shorter than the hypotenuse, and the side opposite the angle is always a factor of sine shorter than the hypotenuse, given the triangle is a right triangle. And it's really cool to know if you draw the graphs for sine and cosine, they will look like this. So here is angle phi. And by the way, I need to introduce the concept of radians, as many people have never really understood it. We're used to there being 360 degrees in a circle. I don't know if you've thought about how annoying the number 360 is, but it is quite an annoying number.
I mean, 100 would have been more than 10.
But for historical reasons, it's been decided that there are 360 angle steps around a circle, and these are called degree steps. And now we need to come up with something a bit smarter. 360 degrees is a full turnaround. What we are utilizing here is that the circumference is a circle. So that means, how far can a wheel roll if it rotates 1 revolution without skidding? It must not spin. That doesn't work.
Take it easy.
Yeah.
So you can imagine here you have the wheel.
And it rolls precisely 1 revolution, so that it ends up over here shortly. And now it will have traveled a distance from there to here, and that distance is called the circumference. Because just as far as it is around, that's as far as it travels if it rotates a full turn here. So the circumference is here. And this circle has a diameter I call d. I don't call it pi. And experiments have shown that how far the wheel travels, if it rotates a full turn without skidding, is always the same, proportional to the diameter, no matter how big the wheel is. So it's believed that the circumference is the diameter times pi. That's how pi is defined, actually. But since diameter is the same as 2 times the radius, you can also write it as 2 times pi.
Like this.
And the circle we're dealing with over here has a radius of 1. So exactly in the unit circle. What about the circumference? It's just 2 pi times 1, which is 2 pi. So if I put a measuring tape around the unit circle, how many meters would there be around the unit circle? 2 pi. 2 pi what? 2 pi meters. But mathematicians don't count units, so just 2 pi. And here's the clever part. Since there are 2 pi distance units all the way around the circle, why not just define that there are also 2 pi angle steps? Then an angle step matches a length step of 1. So it makes everything much easier. So we now define that 360 degrees is the same as 2 pi. Is a new step. We can't call it degrees because we already use the word degrees, so we invent a new word. Where am I talking about? So 2p radians have been defined to be the same as 360 degrees. And now you have to imagine
I'm taking
the angle in radians.
See the
How
sine
like
wave?
these
Well, if
The angle is 0 here. So the point P is down here. What is then y-con?
and remember, Sine, it was the y coordinate.
And right now we are keeping an eye on the y-coordinate. So if the point is here, where the angle is 0, then the y-coordinate becomes 0. So sine starts at 0, 0. I pick the y-axis. That is the y-coordinate of the point P.
What happens when pi starts
So
to
if
worry?
I go up here, the y-coordinate grows from 0 to 1. Can you see that? And when does it become 1? It does when P reaches all the way up here at an angle of 90 degrees. But if 360 degrees is 2 pi radians, then 180 degrees must be half as much. That is pi radians. And that means 90 degrees is pi half radians. So 90 degrees is like this here. Yes, it's pi half radians. So when I get to pi half here. So now I'm up at 1. And the graph looks like this so far. It boxes up and reaches up there in land. And then the graph continues like this. If you just think about it, because this point P moves further and further around, when it reaches up here, the y-coordinate is 1, and now the y-coordinate gets smaller, and here the y-coordinate is 0, and down here the y-coordinate is -1, and back the y-coordinate is 0 again. And that's the curve we've drawn here. So that's the sine curve.
And we can draw a completely corresponding curve from cosine.
It just doesn't start at 0. Cosine starts at 1, because when point P is here, where the angle is 0, the x-coordinate is 1.
And that's why it starts at 1. And the graph looks like this.
Where this is the angle in radians, and this is the x-coordinate to P. So here is my cosine circle, and here is my sine circle.
Are there any questions about that? So the question is, what do you get if you differentiate sine?
Well, if you differentiate sine. I know somebody has come up with the idea that you should call the angle x, and that can be a bit confusing. But typically you call the input to the sine function x, but you should think of x as an angle in radians. And if you differentiate it, then you get, as we'll now try to understand, cosine.
And what does it mean to differentiate?
It means finding the slope of the tangent. So I'll try looking at this graph here. Are there any spots on this curve where the tangent slope is easy to see? Yes, there. And there. It's 0.
And there it's also 0. And can you see? It still
Where the
is.
tangent slope is 0 here, it's exactly where the sinusoidal curve intersects the x-axis and gives 0 as the y value. So it matches that the cosine tells us what the slope of sine is. When we're from here to here, is it going uphill or downhill? It's going uphill. So what's the slope? Is it positive or negative?
Then you go down and look to see that it matches with the cosine. So you think positive
Values.
y.
When I'm between 0 and pi over 2. That's what it is, pi over 2.
So it matches with as the slope tells
It is
the
on the
cosine.
scene. And conversely, if I now ask, what does cosine of x become when differentiated? It turns out you need a sign change to make things add up. It's because the difference of Poisson gives minus sine, and that's why we like sine a bit more than Poisson.
Because there's no sign change when we differentiate.
Let's just take a short break here, and then I think I'll continue for another quarter of an hour afterwards before I write the exercises down, and then we're done for today. Here's a little thought exercise you can tinker with. We've just seen that the circumference of a circle, if I now call it year, then it's 2 times p times the circle's radius. That's how you can figure out the distance around a circle. Now imagine this is the Earth seen from the side.
And it has a radius, which I call Lilaire.
And the Earth's radius,
It is 6,371 kilometers.
now imagine you take a rope and lay it tightly around the Earth. Then you make the rope 1 meter longer than what was needed to go tightly around the Earth, so that the rope could theoretically float a little, if that were possible.
It could float a bit over the entire Earth here. in all weather conditions. There's a bigger radius reaching out to the rope now.
And what we'd like to know is how much my rope could float here. How far is it? We call it x because we don't know it. You have to find x. So your task is, how much can a rope float if it could float around the entire Earth? Assuming the Earth was a perfect sphere with that radius. If you lay a rope tightly around the Earth, make it 1 meter longer and let it float. How much would it be able to float? You should be able to find next. Now we will pause the recording for a bit, and then you try it, and I'll calculate it on the board. Because what you'll see, I think, is why we need to learn mathematics. And before I demonstrate why we need to do math, I just want to ask if there's anyone here who has a good guess, like an intuition, preferably a craftsman, someone with a lot of experience, who might have a suggestion. What would your guess be? A meter. So there's a guess here, x1. We're guessing a meter. Any other guesses? Remember, it has to be completely warm around the Earth. Then we'll make it a meter longer. How much could it float then?
My navel is called All.
And my neighbor, he's quick
Right.
off the mark.
Generally and logically, he's good at arithmetic. Can quickly figure out how much gravel he needs to buy when he's casting concrete and stuff, right? So I told him this one, and he responded. And Olga said, you can surely go home and rethink that. That's wrong. I can just tell you straight up. This is right, Olga. This is how it is, I say.
That's
No.
not it. It's necessary that I calculate an ancestor.
It's quite wildly wrong.
Because he had a completely wrong intuition, I believe, because I trust the math, right?
He still doesn't believe me to this day.
So does anyone else have a guess on how much we can hover?
Come on, someone else must have an idea. By 1 meter. Before we had 40,000 kilometers of rope. Now there are 40,000 kilometers and an extra meter. How much can it hover over the entire Earth? Half a meter. Did someone say 1 millimeter? I also think someone said half a meter. 20 centimeters. That's 0.2 meters. What do you say? You need to guess.
1.5 what? 1.5 meters. Okay.
I can tell you that my neighbor, Olga, guessed that it must be 1,000th of a millimeter. He's good at intuition, so he guessed a very small number because the rope has only gotten a tiny bit longer relative to its length, and it's spread over the entire Earth's circumference. So he thought it couldn't be much. And now you can try to calculate it yourselves, and we'll go around and help you. And then I'll do it on the board when we start recording again, so if you want to stop the recording. All right, let's solve this problem. So the task was to put a rope all the way around the Earth, tight against the surface. The Earth has a radius r, which is 6,371 kilometers. Now imagine that you magically make this rope exactly 1 meter longer, and then stretch it out so it forms another circle, slightly away from the Earth, at a distance of x. You can imagine it hovering a little above the entire Earth. And what do we know now? We know that the circumference of the rope initially has to be the same as the circumference of the Earth, as it was meant to be tightly around the whole globe. And the circumference is a circle, which is 2 times pi times the radius. I don't feel like putting numbers in, because I'd much rather work with symbols.
I'll wait to add the numbers at the very end.
So what happens is this rope is made 1 meter longer. So how long is the rope now?
It's still what it was before. Just remember 1 more meter.
So this number was far around the black circle. The number I'm writing now was far around the dotted circle. And there is also a circle circumference, but it's just the circumference of a circle with radius r. So it becomes 2 pi r. I can now subtract the two equations from one another. If I take this and subtract that from it, what do I get? Okay, so it's the surrounding circumference plus 1 minus the surrounding circumference.
So it must be that one minus that one.
If I say that one minus that one, then I also have to say this one minus that one.
So it must be 2 pi r minus 2 pi r. Yeah. I can now see that the circumference of the circle cancels out, and there's just an innocent one left here. And on the right side, I see that 2 pi is a common factor, so I can put it outside the brackets, following our algebra rules. So it's r minus little r. But what is big R minus little r? It's the difference between this radius and that radius, and that's exactly what I want to find, because it's x, since x is in there.
From here to here, that's x.
So for
It's
example,
precisely the big radius minus the small radius. So I recognize this as x, and that's what I want to find.
so I can isolate x by dividing by 2 pi on both sides. That's how I found the answer.
The rope floats at a distance x of 1 divided by 2 pi. And I measure in meters here, because the rope is made 1 meter longer, and 1 divided by 2 pi is approximately 0.159. So about 15.9 centimeters. About 15.9 centimeters is how much the rope can hover over the earth. And that surprises most people. But interestingly, it didn't surprise this class, because almost all your guesses were
They
spot
were
on.
all very high.
1 meter, half a meter, 0.2 meters, some meters. It's the first time I've ever had a class guess so high. Usually it's like the average guess is about 1 millionth of a meter in a class.
But anyway, as you can see,
If you had the
and
intuition
said it's nothing,
then you were wrong. And that's why we learn math, because you really shouldn't trust your intuition blindly. It can be really good, but it can also be wrong. And I remember so clearly the times I've been wrong, where I was sure I had errors. 2 of the errors have been calculated afterwards. Those are the ones I remember best, in the places where I was wrong. Math is awesome, because it teaches us to be careful about being too sure of our intuition. And there are just some places where intuition isn't enough. Do we agree that we should be too sure of
So I
ourselves?
say 1 plus 2 plus 3. That must be the same as 3 plus 2 plus 1.
And most intuition says, that's logical. You wouldn't tell us otherwise. But something that's not so logical is that it's only true that the order doesn't matter if there's a finite number of numbers. If you're adding an infinite number of numbers, then the order isn't always irrelevant. What?
And the cat plushie.
And that's where you often come in and prove things that you otherwise would have refused to believe, because it's just completely against your intuition. That's why I think one of the reasons I find math super cool, it really expands our ability to think systematically. There's also a little story you have to hear, which I find amusing. It shows the difference between a physicist, an astrophysicist, and a mathematician. On a train through the Netherlands, 3 scientists are sitting and talking to each other in a compartment. And out in the field in the Netherlands, there's a green cow. And the astrophysicist says to the others that they have green cows in the Netherlands. The physicist, who had also seen the cow, says, you can't really say that. You can only say that in the Netherlands, there's at least 1 green cow. Oh, come on, says the mathematician. You can't even say that. Can you guess what the mathematician said? He said, at most, you can say that in the Netherlands, there's at least 1 cow. That's green on at least one side. But they'd only seen the cow from one side. And you see, that's because mathematicians always think in extreme exceptions. They have to be completely sure that they aren't saying too much.
If a mathematician says something,
Then you can be 99.9999% sure that they haven't said too much. So he doesn't want to be a mathematician. That's the kind who likes it. Yeah, they are the ultimate detail-oriented people, the mathematicians. They're the ones who delve into the tiniest details of logic. Obviously, jag vet från mathematics. Jag vet inte vad det är. Det är error. It's usually because you have an answer. Unfortunately. I tried it many times myself. I had a discussion with my old math teacher about calculus, and I was wrong. But I was pretty sure I'd calculated it correctly at first. So let's tackle the last topic for a couple of minutes. It's calculus. I'll just talk for about 2 minutes, then I'll write down the assignment. So stick around for 2 minutes for the intro.
Now comes one of the most important parts of the whole course, and that is understanding calculus. So that's what we're going to start with next time. It's calculus. I wish I'd received this as the very first thing. So I'm telling you this is the very first thing now. Calculus is just about being able to find the slope.
At any given point, on any sphere, on any function.
So that means if I have some function here, it must be from 1.
That's the graph of some function. Differential calculus is about being able to pick any point on the curve. Here, for example, and zoom in with your smartphone at that point until you can't distinguish the curve from a straight line. And that straight line, which it resembles, is called a tangent. And differential calculus is about being able to find the slope of that tangent, no matter where you are, no matter what graph, no matter what function. That's what differential calculus is about. And since slope means how fast you change per f, for a physicist, differential calculus is about finding the instantaneous growth rate, something in relation to something else. That's what it's all about. And we will start on that next time. Thanks for today. And just keep the camera rolling, because I need to write down some tasks. You can also just pause it, and then we'll turn it back on when I've written down the tasks. So just pause it. That's actually fine. Just pause it. So I'll write down while we're paused. Here are some tasks you can work on over the weekend until Monday, September 9th. You need to solve the equations x minus 3 squared equals 0, 3x squared plus 1 equals 0. X minus a half times x plus 3 halves equals 0. The equation x squared plus x minus 6 equals 0. The equation x plus 3 in parentheses times x minus 3 in parentheses equals 0. Another quadratic equation, 2x squared minus 4x equals 0. Another quadratic equation, x squared minus 9x equals 0. And x squared minus 25x equals 0. Next, you'll be graphing the function y equals 2x plus 3. So draw the graph for that. In this task, it says y equals x plus b. So it's a function where the graph is a straight line. You need to determine the slope and the y-intercept. Given that the graph passes through points P1 and P2 with coordinates 1, 3, and 5, 10. In problem 11, you need to calculate cosine squared of 20 degrees plus sine squared of 20 degrees. And this can be done in your head. Problem 12, we need to determine the doubling constant x2 when we have an exponentially growing development, which is 8 times 3.1 to the power of x. And finally, in problem 13, there's a quadratic polynomial called f of x, which is equal to 2x squared minus 8x plus 1. You need to find the vertex and determine if the discriminant is positive, negative, or 0. See you on Monday.